Welcome back, and here we go with the last of the chemistry review for AP Bio, and it's going to be a little bit of hodgepodge of some kind of basic energy stuff, and then getting into the energy of those electrons and how that influences bonding. So what we're going to look at real quick is potential energy. So potential energy is the energy of position or location, so it's stored energy like a battery. In this case here, we've got a rock up on the top of the hill, and that rock has the potential to roll down the hill and release that energy. So an electron is similar to that rock in that it has potential energy due to the position in an atom relative to the nucleus. So the more distant the electrons, they have more potential energy because they want to be closer to the nucleus in order to be stable. So the first shell, if we talk about like a Bohr model of an atom with a nucleus, the first shell around the outside of that would have the lowest potential energy. As we go progressively farther out, the second shell would have more potential energy, the third more, and fourth more. So the further away from the nucleus we get, the more potential energy those electrons have. So to change shells, electrons either have to absorb or release energy. So in order to move out, they've got to absorb energy, and that could be from absorbing a photon being placed in an electrical field. In the case of like a neon lamp, when you turn the electricity on, those electrons are excited to a higher energy level. And to release that energy, they've got to move in. So in this case here, we see this electron is moving into a lower energy level, and in doing that, it will release that energy, usually in the form of a photon that we may see as visible light. So that is the potential energy those electrons have, and as they're moving, the opposite of potential is the kinetic. The kinetic energy is just energy of motion, so anything that has movement involved. So types of energy, and I'm going to go through these kind of quickly. Thermal energy is usually the lowest quality. So when you start up your car, some of the gasoline is converted to heat energy, and that's lost. It's really not usable. If you put your hand on your forehead right now, you should feel a little warm, hopefully not too warm, but that is energy that's going to be lost. We really can't recover that. We can account for it, but we're not going to be able to use it. There's also chemical energy. So chemical energy is like sugar. When you eat something, gasoline, it has the potential to release energy. Solar energy, you all know about solar panels, the sun, nuclear energy, electrical energy. And the one thing that I just want you to remember, excuse me, real quick, is that we can convert just about any form of energy into another. So solar energy can be converted into electrical. Chemical energy can be converted to thermal. Solar can be converted to thermal. Nuclear can be converted to electrical. And I could go on and draw a lot more arrows here, but there are a lot of transformations. And when we get into thermodynamics, which we'll talk about, we'll look at this a little bit more closely. So here's just a quick picture of the same thing, and a little bit easier to understand than my chicken scratch. But again, as energy is absorbed, the electrons will bump into outer energy shells, and then as energy is lost, they will drop down to inner energy shells and release that energy. Okay, so those orbitals become important when we talk about bonding, okay? Because these orbitals are the volume of space where an electron is likely to be found. And this is a very important concept, so important that I think I write the exact same thing a couple slides later here. But the chemical behavior of an atom is determined by the electron configuration in the outermost shell. So you may have heard of valence electrons before. Those are in the outer shell. So in the Bohr model that I have here, we have 1, 2, 3, 4, 5 valence electrons in the outer shell, and that's probably how you addressed them in chemistry last year. Another term that I'm going to introduce is valence, which is a little bit different than the valence electrons. The valence electrons are the outer ones. The valence is the bonding capacity of an atom. So in the case here, we have 1, 2 unpaired valence electrons, 3 unpaired valence electrons. So the valence of this molecule would be equal to 3. So it has the potential to make 3 bonds in this case. So just the difference between valence electrons and valence. Okay, so another just quick diagram. So here we have boron, and again we can see 1, 2, 3 valence electrons. Silicon, similar to carbon, 1, 2, 3, 4 valence electrons. Antimony, 1, 2, 3, 4, 5. So this is taking a look at valence electrons. Okay. Again, here is the Lewis dot structure going across from left to right on the periodic table, and we can see how the valence electrons increases as we go across from lithium, which has 1, beryllium 2, all the way over to neon, which is a noble gas, and it has 8 valence electrons, which means that it's unreactive. And so this is an important pattern to keep in mind as we look at valence electrons. Okay. So real quick, I mentioned Lewis dot structure. So let's look at hydrogen. So hydrogen has 1 valence electron, so we can show that with 1 dot. Okay, and it will form 1 bond. Oxygen has 6 valence electrons. So if we put those around, we have 1, 2, 3, 4, 5, 6. So it has 2 sets of completed electron pairs and 2 unbonded. So it has 6 valence electrons, but has a valence of 2, meaning it will like to form 2 bonds. Nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. But what's its valence? So it has 5 valence electrons, but it has a valence of 3. So it likes to form 3 bonds. And finally, carbon has 4 valence electrons, but it also has a valence of 4, meaning it likes to form 4 bonds. So earlier in this unit we talked about the 4 major elements that make up 96% of living matter. Well, here we go. And if you look, hydrogen likes to form 1 bond, oxygen 2, nitrogen 3, and carbon 4. So we can use this information as we start to form bonds between those different elements. So again, just a recap of what I had said before. So chemical behavior of an atom is determined by the electron configuration in the outermost shell. So if we look at the far left-hand side of the periodic table, hydrogen, lithium, sodium, they all have 1 valence electron. Same thing over on the far right, the noble gases, helium, neon, argon, they all have 8 valence electrons. So there is a pattern to the periodic table. Valence electrons are the outermost electrons. The valence shell is the outermost shell. So just a quick recap of what we've been over. Completed valence shell means that they're unreactive. So helium, neon, argon are inert. Unfilled valence shells are chemically reactive. And then finally, we've got a chemical bond is atoms that share or transfer electrons in order to complete their electron shells. And I think I'm going to wrap up right here and take a quick break before we go into the type of bonds for there. So we'll see you in a couple minutes or maybe a couple days, depending upon when you get to it.